Okay, so in this video I'm going to be going over a past exam question. So we have here a question from, which year is it? Let's have a look. From 2011, and it's called Simple Harmonic Motion, so it's clearly relevant to what we've just been studying. So Brad is working on a scaffold. He ties his bag to a hook, H1, which is here, using a light rope of length 5.5 meters as shown in the diagram. He pulls the bag 0.9 meters to the side and lets it swing. So we can already note that this is the amplitude and this is the length of our pendulum. And we're asked first to show that the time period is 4.70 seconds. So in a show question, we really need to show our working. So we can show that we know the equation first. That's T equals 2 pi square root L over G. And so in this case, that's 2 pi times the square root, we were given the length was 5.5 over G, which is 9.81, because we're assuming he's on Earth here. So we can plug that into our calculator here. So we got 2 times pi times, and then we had 5.5 divided by 9.81, and we want to square root that, and we get 4.7046. 4.7046 seconds, which is approximately equal to 4.70 seconds. Note that when we're asked to show, it's good to give an unrounded number first to show that you've actually calculated it, and then to put the number that they asked for. And then we're asked to calculate the maximum velocity of a swinging bag. Remember that Vmax, I might just pull up the formula sheet here and show you. So on your formula sheet, you are given you're not given the maximum values, but you're given all of these equations for simple harmonic motion. And the maximum displacement is just the amplitude. The maximum velocity is the amplitude times the angular frequency. And the maximum acceleration is amplitude times the angular frequency squared. So Vmax is going to be equal to the amplitude times the angular frequency, which is equal to A times 2 pi over the period, which in this case, the amplitude was 0.9 meters times 2 pi divided by the period that we found here, which was 4.70. So that gives us a maximum velocity of 0.9 times 2 times pi divided by 4.7, which is 1.20 meters per second. So the maximum velocity is 1.20 meters per second. Show on the diagram above where this maximum velocity occurs. Well, we know that maximum velocity occurs at the equilibrium position, so we'll put here max velocity occurs at x. Okay, and then we're asked to explain how the tension in the rope varies as the bag swings. Because we haven't spoken too much about this, but as the bag swings, it moves in a circular arc. And this is really a year 12 concept. We have talked quite a lot about circular motion as well. The faster it moves, the bigger the tension in the rope must be. Oops. And it moves fastest at the bottom. The reason that it has to be bigger tension is because the tension provides the centripetal force. So this is more related to vertical circular motion than it is to simple harmonic motion. So it moves fastest at the bottom, therefore the upwards tension must be greatest at the bottom, because it's got to provide the force to oppose the weight force and the force to pull it upwards, and that we can say tension is smallest at either end. So it varies from a minimum value at max displacement to max value at equilibrium. So this one kind of combines some of the vertical circular motion stuff that we did with the recognition that in simple harmonic motion it's moving fastest at equilibrium. Okay, and you can also see that they've kind of guided your thinking by getting you first to answer this question about maximum velocity first, and then asking this question about circular motion. Okay, D. Explain how the maximum velocity of the bag would change if Brad had used a longer rope to attach his bag to the hook H2, which is a bit higher up. So if you look back at the diagram here, he had another hook here. If you had a longer rope and attached it to there instead, that would increase the length of the pendulum. Okay, so we know, so longer rope would mean period increases as t is equal to 2 pi square root L over G. Okay, so if the period increases, what happens to the maximum velocity? Well, V max is equal to A omega, which is equal to A times 2 pi over T. So if T increases, max velocity would decrease. Okay. For E, we're told that Brad offers his friend Anne a sandwich from his bag, and he lets the bag swing when Anne is 1.4 meters away. So she is 1.4 meters away. Calculate the time between Brad's call and when the bag reaches Anne. So we have it starting here, then it's got to move past equilibrium, and it's got to move. Well, she's not quite at the max position, right? She's only, this distance here is 0.5. And so it's got to move to about here, right? Where this distance here is 0.5. So the bag kind of starts over here at 0.9 meters away. And then it carries on swinging until it's 0.5 meters away. But it's complicated by the fact that her reaction time is 0.4 seconds, is it? So they've really tried to complicate it quite a lot. So the time between Brad's call and when the bag reaches Anne. So he calls to her. Wow, they've deliberately made this quite a tricky one. So he calls to her when the bag is here, right? So that's 0.1 meters. So we really need to know how to interpret this stuff. So then it swings through equilibrium, and then it swings out to her there. Okay, so what we need to know is the time between when he calls to her and when the bag reaches her. So it started off here. He called to her when the phaser will be here, so the bag will be here by that stage. Well, that's 0.1. So we can draw that phasor in there. That's when he calls. And then it reaches her when it is 0.5 meters along here, so there's still 0.4 meters left to go. So this distance here is 0.5. So it reaches her when the phasor is here. Whoops. Here. So we want to know how long it took for the phasor to go from there to there, and then from there to there. So we need to figure out what that total angle is. Alright, so let's do that. This is very definitely an excellence question. So we know that this distance here, this distance, is 0.8 meters. So that's 0.8. And this length of the phasor is 0.9. And so we can figure out what that angle is. And then we need to figure out what this angle is. Let's call it θ1. And that's θ2. And this distance here is 0.5. And this phasor's length is always the same as the amplitude, so that's 0.9. So the reaction time, I think, is just a red herring here, which is a bit annoying. So let's figure out what those two angles are. So from the diagram, θ1 is equal to, well, that's the opposite and the hypotenuse, so it's going to be the inverse sine of 0.8 over 0.9. Let's figure out what that is first. And then we'll take the inverse sine of that. So that angle in radians is 1.09. And θ2, well, here it's again the inverse sine because it's the opposite and the hypotenuse. And this time it's 0.5 over 0.9. And that gives us and then we want to take the inverse sine of that, 0.589 radians. And so we know then that the total angle is equal to 1.09 plus 0.589, which is 1.679. And we know that this must be omega t, right? So omega t must be equal to 1.679. In fact, I'll just write the equation that's relevant here first. So we know that theta over time must be omega, because that's the angular speed of the phasor. So time must be equal to theta over omega, which is equal to 1.679 over, maybe we should work out omega here. So omega is, or did we work it out earlier? Omega equals 2 pi over t, which is, and the time period for the swing was it 5.5 seconds? I think so. Let's go back and check. That was 4.70 seconds. is 2 pi over 4.7, which is 2 times pi divided by 4.7 is 1.34. So that is 679 divided by 1.34 is 1.25 seconds. And we should just check that that sort of makes sense. We know the period is 4.7, and this angle here is going to be, it looks like it's kind of close to a quarter. So it's a little bit more than a quarter actually. And that makes sense, that it should be like a little bit more than a quarter of a period.